Hi, my name's Trin.
Hi, my name is Chao.
And I'm Casey.
This is our Chem 151 video project.
Yay!
And today we'll be talking about the liquid fluoride thorium reactor. Enjoy.
Hello and welcome. Today we'll be talking about the nuclear fuel liquid fluoride thorium, but we can't talk about thorium without first talking about nuclear power in general. Nuclear power is a major world source of electricity and a growing interest as the world attempts to reduce its dependence on fossil fuels. As of May 2016, there are 444 nuclear power plants across 30 countries worldwide, and another 63 new nuclear plants are under construction. Nuclear power accounts for over 11% of the world's energy needs, and thanks to nuclear, 64 billion metric tons of greenhouse gas have been avoided. Currently, uranium-235 is the most common fuel for nuclear power. Now let's take a quick look at how it works. When the nucleus of a uranium-235 atom is struck by a fast-moving neutron, it undergoes a process called fission, meaning it splits in two and throws off some of its own neutrons. If enough of these neutrons are shot off, it causes the nuclei of other nearby uranium atoms to split as well. This releases more neutrons and causes a chain reaction. Each time a uranium atom is split, it creates a huge amount of energy in the form of heat, which can be captured and used to create electricity. When used as a fuel, uranium-235 comes in the form of solid rods that power what is known as a pressurized water reactor. While this does generate lots of power, it does have some disadvantages as well. First off, the fuel rods need to be replaced every few years, which can be very expensive. Also, buildup of fission products such as stuff called xenon-135 lowers the efficiency of the fission reaction, which leads to increased waste and cost. And last but not least, the pressurized water which runs the reactor can be very dangerous. Water serves as an important coolant and helps control neutrons, but in order to do this, the water must be kept at extremely high pressures. This high pressure is both dangerous and expensive. It can cause an explosion if it isn't maintained, and the engineering required to control it is very expensive. And all that aside, uranium isn't even good in terms of efficiency and energy produced. There are much better fuels out there, which brings us to thorium. Thorium is number 90 on the periodic table of elements and was discovered by a man named John Jacob Berzelius, who named it after Thor, the Norse god of thunder and war. Unlike uranium, thorium is known as a fertile fuel because it itself cannot undergo fission when hit with a neutron like uranium does. Instead, when thorium is struck by neutrons, it undergoes a series of nuclear reactions that turns it into an element that does do fission. With this different type of fuel comes a different type of reactor, known as the liquid fluoride thorium reactor, or LFTR for short. The biggest difference between LFTRs and current nuclear reactors is that the fission reaction in LFTRs occurs in molten salt instead of water, making the reaction more efficient while preventing a meltdown. The way it works is the core of a thorium reactor is made up of a uranium core surrounded by a liquid thorium salt blanket. The thorium blanket constantly produces new uranium atoms to fuel the reactor by bombarding the thorium fluoride with neutrons. It should be pointed out that the uranium in this core is different from the uranium we talked about earlier. The thorium core is made up of uranium-233, which is a much better fuel than uranium-235, which is the reason for thorium's superiority. Anyway, since the fission of the uranium in the fuel core produces two neutrons, one neutron can be used to turn a thorium atom from the blanket into a new uranium atom, and the other neutron can be used to split another uranium atom in the reactor, which then generates more energy and two more neutrons. So basically, the reaction keeps itself going without any external help, which makes it much easier to use. Along with everything we just explained, there are even more advantages to thorium. First, thorium is 3 times more abundant than uranium and can be easily mined. Some estimates say it can produce energy at a third the cost of a uranium reactor. Also, it's a liquid fuel, so we don't have to replace the rods every few years, which saves money. Thorium reactors produce much less waste than uranium, and that waste, while admittedly dangerous, stays that way for only 300 years. Which sounds like a long time, but when compared to uranium waste, which stays dangerous for up to 10,000 years, it is a huge advantage. In liquid fuel, unwanted reaction products can be easily removed, while in solid fuel rods, these products are trapped in the structure of the material, which makes the liquid fuel safer and reduces the cost. Another interesting benefit of thorium is that reactors fueled by thorium produce a very distinct and powerful signal, which means that reactors can easily be monitored worldwide via satellite to ensure safety and transparency between nations. Liquid reactors also have built-in safety features which prevent any sort of meltdown. For example, the fuel is contained by a plug that will melt on the off chance that the temperature of the liquid gets too high. If this happens, the liquid fuel can safely drop into a second compartment and cool down without causing any harm. Lastly, unlike uranium-235, thorium fuel is extremely difficult to turn into a bomb, so the threat of this technology being used for weapons is almost non-existent. So, after hearing all this, you might be asking yourself the same thing I did. Why in the world aren't we using thorium instead of uranium? Well, the answer lies in nuclear history. At its beginning, nuclear research was funded by the military with weapons in mind, and so power efficiency was not a priority. So, in the 1950s, when the future of nuclear power was still in question, a Navy admiral named Hyman G. Rickover was the key player in the fate of nuclear power. Rickover's goal was to produce a nuclear engine which could power vessels like submarines and aircraft carriers. While scientists knew about thorium at the time, it would not be ready to go as soon as uranium. Also, a major product of uranium reactors is plutonium, which can easily be made into bombs, and during the Cold War arms race, this was quite desirable. Additionally, molten liquid fuel would not work well on a moving vehicle, so, in the end, Rickover decided on uranium, which won the major funding battle. Uranium technology was then heavily researched and developed on the military's dime, and once the military scientists who developed this technology left the government, they continued producing the same uranium reactors in civilian power plants, since that was the technology they knew best. Uranium quickly became the only option by default, and until recently, there was no real incentive to change or improve this technology, especially considering public disapproval of nuclear power. But, now that we see the dangers of global warming and over-reliance on fossil fuels, all forms of alternative energy are being re-evaluated, including thorium. Which brings us to present day, and what is in store for thorium. Currently, India, China, and France are the leading countries in terms of thorium research, and in the US, the Department of Energy has just issued 2 awards to further research on liquid nuclear reactors. So, as the world's energy demands grow and fossil fuel reserves diminish, the liquid fluoride thorium reactor is a promising technology that could help protect the planet while safely maintaining our way of life.